Imagine you are standing on the edge of a precipice, staring down into an abyss so profound that it could easily swallow the tallest mountains on Earth and still leave kilometers of dark, freezing water above their highest peaks. You are looking at the Hadal Zone, the absolute bottom of our planet, plunging to depths of nearly 11 kilometers. If you were to physically descend into this ink-black void, dropping past the twilight zone and into the crushing, claustrophobic depths of the oceanic trenches, you would enter an environment defined by extreme, unrelenting deprivation. The ambient temperature hovers just above freezing, stalling indefinitely between 1 and 3 degrees Celsius. The hydrostatic pressure is utterly immense, reaching up to 1,000 atmospheres, a physical force roughly equivalent to the weight of several commercial jumbo jets resting on every single square inch of your fragile body. Down here, there is absolutely no sunlight to drive the life-giving process of photosynthesis. There are no changing seasons to signal the passage of time. And perhaps most frustratingly, there is almost no food. Logic and our fundamental understanding of terrestrial biology dictates that any living creature surviving in this desolate, high-pressure wasteland should be tiny, starved, and stunted. They should be conserving every microscopic fraction of energy just to keep their internal organs functioning. But nature, as you are about to discover, possesses a profoundly twisted sense of humor. Instead of finding a realm of microscopic scavengers, we find that this pitch-black, frozen purgatory is ruled by undeniable titans. We call this biological anomaly deep-sea gigantism. But even among these giants, there is an invisible barrier. If you look closely at the distribution of life in the ocean, you will notice a bizarre, unsettling pattern. While bacteria, viruses, and heavily armored crustaceans thrive at the very bottom of the Challenger Deep, the most successful and adaptable group of vertebrates on Earth, fish, abruptly vanishes before they can reach the bottom. There is a precise, invisible boundary line, a biochemical wall located miles beneath the surface, past which no fish can ever swim. By the end of this journey, you will understand the exact chemical lock that bars the gates of the deepest abyss to the world of fish, and why this biochemical ceiling is an impassable, eternal law of nature. To comprehend the true scale of this biological wall, we must first look at the stakes of the journey. The oceans cover more than 70% of our planet, and their average depth is nearly 4 kilometers. But the trenches are a different world entirely. If you were to drop Mount Everest into the Challenger Deep, its snow-capped summit would still be covered by more than 2,000 meters of water. The pressure at the bottom of these trenches is not merely high, it is a physical weapon of mass destruction. At 1,000 atmospheres, the very physical properties of water begin to change. Under normal conditions on the surface of the Earth, water molecules form a stable, loose network that resembles a tetrahedron. But as you descend past 6,000 meters, the immense weight of the water column squeezes these molecules, distorting their hydrogen bonds and forcing them into a dense, unstable state. This pressurized water is incredibly aggressive. It does not just crush spaces. It forces its way into the intimate, microscopic structures of living cells. It invades the folded structures of proteins, the very machinery of life, disrupting the delicate hydrogen bonds that keep them in shape. Once a protein loses its shape, it denatures. It flattens out, stops functioning, and the cell dies. For any vertebrate from the surface, a descent into this abyss would not just crush their bones, it would instantly liquefy their cellular machinery. Yet, against all imaginable odds, some fish have managed to push deeper than anyone thought possible. In the deepest trenches of the Pacific, scientists have discovered the Hadal snailfish, a pale, scaleless, and almost translucent creature that looks more like a ghost than a predator. These bizarre animals do not just visit the trenches, they thrive there. They are the apex predators of their extreme realm, actively hunting, reproducing, and living at depths of over 7,900 meters. They are living testaments to the incredible plasticity of vertebrate life, surviving in a high-pressure, freezing purgatory that would instantly destroy any human-built submersible. Their dominance at these depths is awe-inspiring, suggesting that, with enough evolutionary time, fish could eventually conquer the entire ocean, all the way to the very bottom of the Challenger Deep. But they cannot. Just as they seem poised to claim the absolute depths, they hit a wall. Near the boundary of 8,200 meters, the fish simply disappear. No matter how many expeditions we send, no matter how many traps we set, we find absolutely nothing but empty water and armored crustaceans below this line. The fish are trapped, locked out of the deepest 25% of their own ocean by an invisible, lethal constraint. To understand why this wall exists, we must pivot our focus away from the ghost-like silhouettes of these snailfish and look deep within their cells. We must examine the secret weapon that allows them to survive at 8,000 meters and how that very weapon eventually becomes their executioner. In the mid-20th century, researchers discovered that deep-sea organisms contain high concentrations of a strange, fishy-smelling compound called trimethylamine N-oxide, commonly abbreviated as TMAO. For decades, TMAO was thought to be nothing more than a waste product, the substance responsible for the characteristic smell of rotting fish on a fishmonger's stall. But recent research, including advanced neutron beam analysis conducted at the University of Leeds and the ISIS neutron and muon source, has revealed a brilliant, counterintuitive truth. TMAO is a piezolyte, a specialized molecular shield. Under the crushing pressure of the deep sea, where water molecules are forced into the delicate folds of proteins, TMAO acts as a structural anchor. It binds tightly to water molecules, strengthening their hydrogen bonds and preventing the aggressive, pressurized water from invading and collapsing the protein structure. It is a chemical chaperone, ensuring that the machinery of life can continue to fold and function normally, even under hundreds of atmospheres of pressure. The mathematics of this survival strategy are incredibly precise. Scientists have discovered a direct, linear relationship between the depth at which a fish lives and the amount of TMAO accumulated in its muscles. Shallow water fish, living near the sunlit surface, have almost no TMAO in their systems. But as you trace fish species deeper and deeper down the oceanic slopes, the concentration of TMAO rises steadily. By the time you reach the Hadal snailfish, captured at a record-breaking depth of 7,000 meters in the Kermadec Trench, the concentration of TMAO in its muscle tissue is astronomically high, measuring nearly 400 millimoles per kilogram. This represents an osmolyte protection ratio that is perfectly calibrated to withstand the immense physical force of the surrounding water. It is a stunning evolutionary achievement. But this molecular armor is not free. It comes with a devastating, inescapable catch that completely rewrites the rules of deep-sea survival. To accumulate these massive quantities of TMAO inside its cells, the fish must fundamentally alter the chemistry of its bodily fluids, setting off a slow, biochemical time bomb that is ticking with every meter of descent. The ultimate reveal of this biological mystery lies in a basic physical process that every living cell must perform: osmoregulation. The cells of all bony fish are hypoosmotic relative to the surrounding ocean. This means that the concentration of dissolved salts and molecules inside the fish's body is significantly lower than the concentration in the salty seawater around them. Typically, a marine fish maintains an internal osmolality of about 350 milliosmoles per kilogram, while the surrounding seawater has a highly concentrated osmolality of approximately 1,100 milliosmoles per kilogram. Because of this massive difference, water is constantly trying to escape from the fish's body through osmosis, and the fish must expend precious energy to retain its internal fluids and prevent dehydration. When a fish descends into the deep ocean and begins to accumulate TMAO to protect its proteins from pressure, these molecules do not exist in a vacuum. TMAO is an active osmolyte. Every single molecule of TMAO added to the cell artificially raises the internal osmolality of the fish's fluids. As the snailfish descends deeper, accumulating more and more TMAO, its internal osmolality begins to climb, narrowing the gap between the fish and the sea. In the Kermadec snailfish, captured at 7,000 meters, the massive accumulation of TMAO drives its internal osmolality up to an unprecedented 991 milliosmoles per kilogram, nearly 3 times higher than a shallow water fish. By extrapolating this direct, linear chemical trend, scientists have discovered a terrifying mathematical certainty. Between the depths of 8,200 and 8,400 meters, the internal osmolality of the fish's body will reach exactly 1,100 milliosmoles per kilogram. At this precise point, the fish becomes perfectly isosmotic with the surrounding seawater. If the fish attempts to descend even a single meter deeper, it would have to accumulate even more TMAO to protect its proteins, pushing its internal osmolality past the threshold of the ocean. The fish would become hyperosmotic relative to the sea. To survive in this state, the fish would have to completely reorganize its entire osmoregulatory system. It would have to stop drinking seawater and instead begin actively filtering and excreting excess water from its tissues. To do this, the fish would need to redevelop complex kidneys equipped with functioning filtering units called glomeruli, organs that marine bony fish abandoned and deactivated hundreds of millions of years ago when their ancestors transitioned from fresh water to the oceans. The evolutionary clock cannot simply be run backward. A fish cannot completely rewrite its ancient, deep-seated physiology while swimming in a freezing, high-pressure desert. This is the absolute, unyielding biochemical ceiling. It is a hard, physical wall built from the fundamental laws of physical chemistry, forever barring fish from the deepest 25% of the world's oceans. This impassable biochemical limit serves as a dark, sobering mirror for humanity, forcing us to confront our own fragile place in a rapidly changing world. We are accustomed to viewing life as an infinitely adaptable force, a resilient mechanism capable of overcoming any obstacle given enough evolutionary time. We look at the extreme environments of our planet and marvel at the survival of extremophiles, believing that nature will always find a way. But the absolute boundary of the fish reveals a quiet, humbling truth. Even the most successful and adaptable lineages on Earth have hard, non-negotiable physical limits. The laws of physical chemistry are absolute, and no amount of evolutionary pressure can force a cell to bypass them. But there is a deeper, more immediate tragedy unfolding in this story. The stable, cold and oxygen-rich deep ocean that has allowed these Hadal snailfish to delicately balance their internal chemistry for millions of years is no longer safe from our influence. We live on the sunlit surface, miles above the trenches, yet our industrial actions are directly threatening this fragile sanctuary. As we continue to saturate the atmosphere with greenhouse gases, the oceans are absorbing the vast majority of this excess heat. This warming is not confined to the surface, it is inexorably creeping downward, altering the temperature and salinity of the deep ocean currents. As the water warms, its physical ability to hold dissolved oxygen plummets, and the vital global currents that pump oxygen into the abyss are beginning to slow down. The deep sea is slowly, quietly suffocating. For the Hadal snailfish, which must maintain an incredibly delicate, high-stakes balance between pressure protection, osmotic pressure, and oxygen intake, this warming is a death sentence. Their enormous, highly specialized bodies are perfectly adapted to a world that has remained unchanged for epochs. But they are completely defenseless against the rapid, human-induced changes raining down from the surface. When we look down into the 11-kilometer depths of the Mariana Trench, we are not looking at a sterile, disconnected wilderness. We are looking at a mirror of our own global footprint. If our careless actions on the surface can reach down into the deepest, most isolated sanctuary on Earth and quietly suffocate the most resilient survivors of the abyss, we must ask ourselves what hope remains for the rest of our fragile, interconnected biosphere.